two meteors crossed Earth's skies. One fell over Peru in 2022, and another passed above the Arctic in 2025. Both were traveling so fast they could not have come from our own solar system. These events were hidden in government data, unnoticed until scientists found an unexplained anomaly. If true, this means material from another star system struck our planet. How did these interstellar visitors go missed until now? NASA's Center for Near-Earth Object Studies, known as CNEOS and spoken as CNEOS, keeps a global record of fireballs entering Earth's atmosphere. In this database, two entries stand out by their identifiers, CNEOS 22 and CNEOS 25. CNEOS 22 refers to a meteor detected in July 2022, with its entry point off the coast of Peru over the Pacific Ocean. CNEOS 25 marks another event. In February 2025, above the icy waters of the Arctic Barents Sea. These catalogue names are more than just labels. Each entry ties to a precise date and location, anchoring the events in official records. Both were recorded not by telescopes, but through government sensor networks. Their details were logged quietly in the CNEOS Fireball database. At Earth's distance from the Sun, there is a hard limit on how fast something can travel and still remain part of our solar system. This limit is known as the escape velocity. For our planet's orbit, that number is 42 kilometers per second. Anything moving slower than this is held by the Sun's gravity, bound to circle the star in some kind of orbit. But if an object moves faster than 42 kilometers per second, it has enough energy to break free from the Sun entirely. It will not loop back. It is on a one-way trip out of the solar system. This single number, 42 kilometers per second, acts as a dividing line. It is the benchmark scientists use to judge whether an object could be interstellar in origin or just another visitor from within our own solar neighborhood. To test whether these meteors truly exceeded the Sun's grip, scientists ran extensive statistical simulations. They ran millions of trials, each time nudging the measured speeds and directions within the known uncertainty ranges of the sensor data. In every run, the outcome stayed the same. Neither object's path could be made to curve back into a solar orbit. Not a single simulation placed them under the Sun's control. The results did not rely on a single measurement. They held up against every possible variation allowed by the data. An on-screen caption states simulated millions of times within measured uncertainties, all trials unbound. This level of analysis gives researchers high confidence that these meteors were moving too fast to be products of our solar system. Objects traveling faster than the Sun's escape velocity are not just rare, they belong to a different class altogether. Most interstellar visitors we have confirmed, like Oumuamua in 2017, 2E Borisov in 2019, and 3I Atlas in 2025, were tracked by telescopes as they passed through the solar system. These objects were large enough to reflect sunlight, revealing their presence long before they came close to Earth. In contrast, the meteors identified by atmospheric entry were much smaller, too faint to spot until they collided with our planet's atmosphere. This means that while telescope-detected interstellar objects offer a chance to study their paths and composition in detail, the smaller, faster meteors announce themselves only in a brief burst of light and energy, often leaving no trace behind. Both types, however, share one defining trait. Their speed proves they are not from here. Oceanographers studying the 2022 Pacific event point to the vast depth of water off the coast of Peru, often plunging several thousand meters. In such an environment, even the largest fragments would be nearly impossible to retrieve. The seafloor here is rugged and remote, far beyond the reach of most recovery missions. For the 2025 Barents Sea meteor, the situation is different, but hardly simple. The Arctic's shallower continental shelf, with depths closer to 300 or 400 meters, offers a better chance for fragments to settle within reach of specialized equipment. Yet, shifting sea ice and strong currents can quickly scatter debris across the seabed. Any attempt to recover material would require precise timing, detailed mapping, and a coordinated effort between marine scientists and polar logistics teams. These practical barriers make the recovery of interstellar material an extraordinary challenge, even when the impact occurs in more accessible waters. Most small meteors burn up in the atmosphere without ever being noticed. The fact that two possible interstellar objects were found by searching through existing sensor archives raises an important question. How many more have slipped by, unrecognized? Earth is constantly monitored by a patchwork of government and scientific sensors, yet much of the planet's surface, oceans, polar regions, and remote deserts remains outside the reach of dedicated sky surveys. The CNEOS database only captures fireballs bright enough to trigger satellite alarms or ground-based detectors. Many fainter events, and those over blind spots, leave no record at all. Scientists have begun mining old datasets, looking for overlooked high-speed entries. Each new detection depends on careful reanalysis, not on new technology. With every candidate discovered, the sense grows that interstellar material may be arriving more often than the official count suggests. The story of these meteors is incomplete. It may only hint at a much larger flow of cosmic debris passing through our skies. Today, interstellar material slips through our skies almost unseen. Each detection sharpens our sense of cosmic connection and reminds us how much of the universe still waits, unnoticed above.